Hi pre-calculus friends, here we are with graphing linear equations in section 1-3. So let's jump right in here with our vocabulary for this section. We're going to start off with the concept of linear equation. And what a linear equation is basically an equation that's going to give us a line when we graph it on the x and y axis. And they can be in a number of forms. You may remember these from previous math classes, but what we have here is slope-intercept form of a line, standard form of a line, and point slope. Sometimes standard is called general, depending on the textbook. But for us, we'll call it standard. And so when you have these different forms, basically, if you have an equation that can be written in any of these forms, then you have a linear equation. And so you might remember linear equations. Oftentimes we graph them. I'm going to actually have a couple of these. Let's see. Okay, so I've got 4 coordinate planes here that I just wanted to say, if you have a graph that looks like this, that's a linear equation. And basically there's 4 ways that we'll see them, either going up to the right, down to the left, horizontal, or we might even have vertical linear equations, okay? So these are the things that we're going to see. I'm going to actually shrink this for now and talk a little bit about it later. All right, so I'm losing too much stuff. Let's find it. Let's fix it. So what we're going to talk about next, now that we have kind of an idea, hopefully remember linear equations, what we'll talk about now is a little bit of the relationships that go into it. So again, if I'm dealing with a graph on the coordinate plane that happens to be a linear equation, like this one, there are certain noticeable qualities, I guess we could say, that the graph has. So in this case, you're going to see that this graph has an x-intercept. It is where the graph crosses the x-axis. So the x-intercept is displayed here by this dot here. And then sometimes you can have a y-intercept. And a y-intercept is exactly what you think, where the graph crosses the y-axis. So the x and y-intercepts are very important traits when we're talking about a linear equation. And next we're going to talk about slope. So I'm going to go back and grab these 4 examples. And slope is another quality of a line or of a linear equation. So in this case, we have a positive slope. When the graph goes up to the right, we consider that a positive slope. So slope, the variable we use for slope is m. So m is positive here. And here when we're going down to the right, we know we have a negative slope, so m is negative. In a case like this, where we have a horizontal line, we can tell that this slope is 0. So m is equal to 0 here. And when we have a situation like this, where we have a vertical line, m is undefined. All right? And we'll get into this example hopefully a little bit more later. So these are the different kinds of slopes. It's a quality of the graph. There's lots of ways of talking about it. Sometimes we say m, sometimes we talk about the rise over the run. All right, I hope a lot of this is like pulling back some fog from your minds and you're remembering this. Sometimes we even refer to it. If you give me 2 points, I can find the slope of a line by doing y sub 2 minus y sub 1 over x sub 2 minus x sub 1. All of this goes into the concept of slope. So I want you guys to actually have this memorized. I want you to know when you're looking at a positive slope, a linear equation that has a positive slope, negative slope, 0 slope, and an undefined slope. So here you can see we're bringing up the concepts that we talked about before. Standard form. Standard form is just what you think it is. It's just a way that the line can be written, the equation of the line can be written, and it's in ax plus by equals c form. And there's a couple caveats here. A, b, and c all must be integers. So I'm going to write that in this way. A, b, and c must be elements of the integers. Okay, they all must be integers. Specifically, a is generally expected to be greater than 0, meaning a has to be positive. So when you're writing something in standard form, make sure that everything that you're dealing with is an integer, is a whole number, is an integer, and that a is positive. Slope-intercept form is that really cool form that most students really enjoy. I'm going to write about it right here. Right here we have it y equals mx plus b. The beauty of slope-intercept form is that you get so much information about your equation just by looking at it. So m is going to be the slope, and b is going to be the y-intercept. And so just by having this equation, you know pretty much what your graph looks like. So that's why students really love this form, and most people do. So now we're going to talk about this other concept called linear functions. A linear function is going to be a linear equation that honestly only meets these three criteria, okay? This guy's not a function. It fails the vertical line test if you're thinking about that, right? So when you have a vertical line as a graph, it is not actually a function. So when we're talking about linear functions, visually, we're only referring to these three types of graph. But the way that function might be written would be f of x is equal to some mx plus b. And so we're emphasizing the functionness of the linear equation. I'm using the slope-intercept form just because it's convenient, but basically you would have y by itself, or the function value by itself, is equal to mx plus b. Can't really write this in function notation because putting an x and then an f of x here would be awkward and not standard. So linear functions are generally going to be solved for y, or the f of x notation, or g of x, or whatever, and then you will see how x is played out in defining that particular f function. So zeros of a function, interestingly enough, zeros of a function are the values that would make the function zero. But zeros of the function visually will also be, I'm going to show you, will also be the x-intercepts. So let's say I had this function, and so I'm actually going to talk about not just linear functions. Let's say I had a funky sine function, and we'll talk about that later. The zeros of that sine function would be all the places that that graph crosses the x-axis rather. So the zeros are the values of x that make the function zero, that make the whole function zero, that makes the y value zero. Hopefully that's kind of making sense, because when y is zero, we're at the x-axis, right? So that's why it's called a zero of the function. And if we're dealing with a linear function in that situation, let me use that line, and I'm going to go ahead and graph it this way. The zero of this function would be exactly as you think. It would be the x-intercept. So zeros of a function are the x-intercept. Specifically, they're the values of x that make your function equal zero. And finally, a constant function. The constant function is actually this guy over here. It's kind of thick and dark. Let me get a thinner pen. And so the constant function, when we're talking about the constant function, we're talking about a function that would be like this. Y is equal to a certain number, 3, a constant, a number that doesn't change, not a variable. Notice x is not in the constant function situation. Or you can write f of x, the function of x, is equal to 7, or some number. Notice that even though there's an x here, it still has a 7. What does this mean? It means when you see it like this, it doesn't matter what x is, y is going to be 7. Same thing here. Y is equal to 3. I don't care what x is. So how would I graph that? I'm glad you asked. So I'm going to graph both of these. Let me change the color of one so we can get a little bit of a distinction. So the function I'll color, let's say blue, and this other one I will color in, I don't know, yellow. Too bright. Let's go with pink. All right, so when I have this pink function, this pink equation that I'm going to be graphing, I go 1, 2, 3 along the y-axis, and I simply draw a horizontal line. That's it. And if it's the other one that I'm dealing with, then obviously you guys know I'm going to go up to 1, 2, 3, 4, 5, 6, 7, and draw a horizontal line. And that's how we draw constant functions. You know you got a constant function if it's a horizontal line. Example 1 asks us to graph this equation, 3x minus y minus 2, which is equal to 0. And they want us to use x and y intercepts. And we can do that. Let's first think about what x and y intercepts are, though. From our definition earlier, we said the x-intercept is where the graph crosses the x-axis, and the y-intercept is where the graph crosses the y-axis, which is very true. When we're dealing with actually thinking about the x and y-intercept, I want you to also consider it in terms of the equation. The x-intercept is the value of x when y is 0. The y-intercept, let me write that down, this is the x-intercept. And the y-intercept is the value of y when x is equal to 0. So you notice I put a 0 there. So this would be the y-intercept. And so Knowing that we only need 2 points to form a line, let's go ahead and find the x and y intercept. First thing we're going to do is substitute in 0 for y. When I plug in my 0 for y, I end up with 3x minus 2 equals 0. Therefore, 3x has to equal a positive 2, and x equals 2/3. So that's my x-intercept. My y-intercept I'm going to find by actually substituting in 0 for x. So when I do that, I'm left with 0 minus y minus 2 is equal to 0. Or I can look at this by bringing the y to the other side. Negative 2 is equal to a positive y. Y is equal to negative 2. This is not that great of a fraction that you want to graph, but I think we can handle it. We're tough. Zooming in a little bit closer, I'm going to come over here and estimate where 2/3 is. If this is 1, as I want you to assume, then 2/3 would be right about there. So 2/3 is that point there. That's the x-intercept. And the y-intercept is down here at negative 2. And so now that I have 2 points to the line, I don't need to do anything else. I totally can graph that line. Let's see how neat I can be. Boom. Pretty amazing. So this was the beginning of the chapter, a little bit of information to get us kind of started thinking about rates of change, which is another way of referring to slope. I'm going to ask you to pause me and read this to yourself so we can get started with this problem. Hopefully it made sense what you read, a lot of information here, but the meat and potatoes of the problem is down here. In 1900, the percent of American workers who were farmers was this amount. So we have these two numbers coinciding together. And then we have in 1994 that this is the number or the percentage of people that were farmers. What the key phrase here is the question. What is the average rate of decline? And average rate of decline or rate of change is another way of talking about the slope. So we're talking about the slope here. And what I want you to see is those two highlighted numbers, 1900 and 37.5, kind of make an x and y point. X being the time and y being the percentage of people that are farmers. And then similarly, we will write the other point, not 1995, 1994. We write the other point in the same way. And so what we're going to do is utilize one of those formulas that you remember from before, the slope formula, or the value of the slope being the change of y's over the change of x. So I'm going to deal with the change of y's. And remember, it's important to start with the same point when you are doing this. So I'm using 37.5 minus 2.5, and now I have to use 1900 because I started with its partner, 37.5, minus 1994. When I calculate this, I get 35% over negative 94. This negative lets me know that I have a negative slope and therefore I have a decline. And we already knew that just by giving the question and by our common sense, recognizing that's happening. So what we want really is a yearly rate. So now what we're going to do is we can pull out a calculator and divide 35 by 94. When we do that, we get 0.37% decline per year. And I should put a negative here. So the way you might write this is 0.37 over 1. It's approximately, it had a couple other numbers after the decimal point, but I rounded it there. And so you might have 0.37% decline per year, something like this, to make it a little bit more rise over runish, or a little bit more slope-like. Let's look at another example. So we're probably going to need another video to finish this, but let's just take a look at where we're going. In example 3, we're going to be graphing using the y-intercept and the slope, so the slope and y-intercept form of a line, as you can see. We're going to turn this equation into slope-intercept form to make it easier to graph. And then finally, we'll discuss a little bit about the 4 graphs that I want you guys to memorize. And then finally, we'll have our last example, which gives us an opportunity to find the zeros of the function. Then we'll graph them. So with that in mind, I look forward to seeing you guys in the next video. Take it easy, and let's finish up this section. Bye-bye.